So let's begin. Once again, we want to start by looking at probability. Okay, we will look at the basics. We'll use some couple of Venn diagrams, and then we'll look at common rules of probability. Next time, we will then be doing conditional probability. In fact, we'll do conditional probability today if there's time. And then we'll look at statistically independent, and more importantly, the Bayesian theory, the Thomas Bayesian theory. All right, I'm going to go a bit slow because I really want you to get the fundamentals. And I know some of you are good, so bring your goodness to the class, and then others can get a picture. So first thing, what do we mean when we say something is random? Anybody can tell me. Raise your hand and tell me, what do we mean when we say something is random? It happens randomly. It can happen at random. What does that mean? What does that mean? It happens randomly. It can happen at random. Oh, by the way, please tell all your colleagues who are not here to please log on and be here. Some of them have gone off because of the time delay. They should be here. It's compulsory. Okay. All right, what does it mean? Random. Something that is happening randomly. Random. Anil, Benedict, Benjamin.
Out of the blue.
Out of the blue. That is a typical translation from Twi to English, right?
Yes, please.
Yes. Out of the blue. Something that is random. Okay? There is no format. There is no pattern. There is no organization. There is no plan. It just happens. Out of the blue, he says. Okay? The basic outcome of something is the outcome of a random experiment. So let's watch it. A random experiment is an experiment that you are not certain of the outcome. Any experiment you are not certain of the outcome is a random experiment. And there are quite examples. Who can give me an example of an experiment that you are not certain of the outcome? Zoe.
Tossing a coin.
Toss of a coin. Very good. Another experiment. Another experiment. Miss Watson.
A football match.
A football match, very true. But there's some kind of football match, if you don't take care, you can tell. Like Ghana going to play Brazil. Are you sure you are not certain of the outcome? The fact that you smile means that you are sort of certain of the outcome, aren't you? So let's get some that are quite debatable, that are not debatable. But don't worry, if it is debatable, your colleagues will tell you. Philip.
Giving birth.
Giving birth. You're not certain of the outcome?
Whether the gender of the child.
Oh, okay. The gender of the child. That's what you mean. Okay, I get that part. You're not certain of the gender. Some people can do it some way. They can actually make the gender happen the way they want. You know that? You've not heard of that?
Yes, but
if you've not heard of that from your father, ask your uncle. Your uncle can give you an idea. But it happens. Anyway, who can give me another example?
Rolling a die.
Rolling a die, very good. Anyway, so you get a point, okay? The probability of an event is anything that can happen out of the sample space. The sample space is a universal set. You may have learned this before. Now let's look at something here. The intersection of two events, if you have two events, okay, and when I say event, is something that happens within the sample space. Then when you have two events, say event A and event B, and they are all within the sample space, the universal space, an intersection of them is the set of all the outcomes in the universal set, but they belong to both A and B. In the form of a Venn diagram, how will it look like? How will it look like? It will look like such that the event A circle will cross over to event B circle. Okay, some portion of the event A circle will cross over to event B circle like this. But there's something you got to know here. There's something you got to know here. If I want to know the universal set here, it will be made up of what? From what you are seeing here, the universal set will be made up of what?
Of
Zoe.
It'll be made up of A and B, B and also S.
Good. That is S outside the event. Now, let me ask you this. What if you do not want to include the A intersection B in your definition? What will the universal set be like? What will the sample space be made of? If you don't want to include the word A intersection B, what can you include? Yes, Philip.
so that would be A plus B plus S.
No, it cannot be A plus B plus S. It cannot be. It's tricky though. Watson.
Okay, so A only, B only, S.
A only, B only, S. Still, no. Now remember that that word A only, in fact, otherwise I would even go for the guy who spoke the first one. A only, B only, S, no. But I will go for the one who said A. But I think that the one who said A did not mean, meant A only. That is why I also said no. So who can polish this? The one who said A, I know the person meant A only. That's why I said no. Kingsley.
Okay, Doc, I feel S would be equal to A plus
Not
B.
S will be. Okay, you mean the universal set, right?
Exactly.
Okay, will be.
That's S will be A plus B.
Okay, where A here means what? Because A plus B is wrong.
Okay.
Right.
I think to be A complement plus B complement plus S.
Say that again. I love that.
I think,
but you see, you're introducing a new term which they don't understand. Yeah.
so the A complement is items in, I mean, just A without the intersection.
I know. But again, you can't say A complement and B complement. Because A complement will be, yeah, Zoe.
Doc, I would say that the universal set would be the union of A and B plus S.
Oh, no, some people have said that already. Okay, so it's a union of A and B only. Oh, by the way, that S there is the universal set. So I don't want you to include that S as if it's outside the Venn diagram. Okay, I want you to see the S as the universal set here. So you cannot include it. Assume that there is no empty set. There is no the section of A, B, and C. That if you take out the circles, there is nothing outside the circles that is a number, so it's zero. I want you to assume that there is nobody who is, in the event of A and B. I just wanted to know that. There is nothing of anybody who is neither in any of the events. So outside of the circle is zero. Yes, go ahead. So with that in mind,
I was thinking, can it be referred to as a disjoint set since they are not related?
okay, so let me draw something here to help you guys, okay? So this is what I mean. This is what you have here. Now you have A intersection B in the middle here, A intersection B. Okay. You have A here. This A here is A only. But then I can say A, which is not A only. This B here is B only. But I can say B, which is not B only. It is B. So there's a difference between B and B only. B only are those that are just within the premise of B, in the event of B, but B are those that can be B only and those that are both B and A. Does that make sense? Salas, your hand is up. And in this case,
I was going to answer, but you have already said it.
Ayo, Bailey. Okay. And in this case, if I bring something like K here, K are those that are neither within the event of A and B. They are neither within the event of A and B. But I want to say that K is 0. Let's assume that K is 0. That's the point I was saying. So the S here is the same as the universal set. So those of you who are including the S is the entire rectangle. So you cannot include it. Maybe you are thinking that S is the K, but I want you to assume that in this context, I've not indicated anybody who is in neither A or B. And who is neither A nor B, and therefore K is 0. Okay, so do not include anything outside of Venn diagram, outside the circles. Now let's focus on what is inside the circle, assuming that everything outside the circle is 0. Then in that case, this A here will be A only, but this A here will be A, but this A there will be A only. Okay, and then we have this to be B, and this B will be B only. So on the basis of that, the universal set will be what? It will be A, and by A, I'm not talking about A only. It will be A plus B only. Take a note. You cannot say A plus B. You cannot say A plus B because the moment you do B, B has already been captured by A. A portion of B, which is the A and B, has been captured by A. And I'm not talking about A only. I'm talking about A. And therefore, you cannot count that again. So the universal set is going to be A plus B only. And I'm not talking about A only plus B only. No, I'm talking about A plus B only. Because remember that A captures this section, which includes A intersection B. I hope you get it. If you don't get it, let me know. Yes, Salasi.
So does that mean you can also say that the universal set will be A only plus B?
Exactly, perfect. You can say that. Now you got a picture. It can be A only plus B. Excellent. You got in it. You got in it. Yes, Watson.
So can we also say then that A only plus B only plus the A intersection B is the universal set?
Perfect. You can say the same thing. Okay. That is where we began from, anyway. So that's it. You guys are cracking it. All right. For those of you who didn't ask the question, it means you fully get it. Let's box on. Now, we can talk about some terms in probability, like mutually exclusive terms. It's simple. When two events are mutually exclusive, it simply means that the occurrence of one precludes the occurrence of the other. Okay? Two events are mutually exclusive. In other words, they cannot happen at the same time. If you look at A and B, they are not connected in any way. Give me two events that are mutually exclusive right now, right here. You can give me two events that are mutually exclusive right now, right here. Give me one, any event. For example, you cannot, okay. And by the way, whichever one you say, okay, it should be non-debatable. Your colleagues should not debate you. Okay. So let's take an example. Right now, you cannot be in US, in Los Angeles, and be in Ghana at the same time. Okay. So I can say that being in the USA and Ghana are mutually exclusive events. I've given you an example. Who can give me another example? And please note that the mutually exclusive event means that the intersection is empty set. Okay. And one way of displaying an empty set is something like that. Yes, Salasi, give me one.
Doc, so that means we having this meeting, there are other groups having another meeting. We can't be in this meeting and still be in the other meeting.
Are you sure, Salasi? Somebody will debate you.
Yes, Prof.
Somebody can have his mobile phone and his laptop listening to both. Ruth, give me some.
Okay, Doc. So, winning a game and losing a game, it cannot happen at the same time.
Super.
You either win or lose.
Ah, I love that. That is excellent. It's non-debatable. Unless somebody can debate it, bring it out and let's see. Clifford.
So tossing off a coin, it's either heads or tails.
That's it. That one is an easy one. Easy peasy. Flip.
Rolling a dice.
Please, nobody should talk about this two again because I think that is too common. Okay. I wanted a very practical one, real life one than rolling a dice and toss off a coin. Yes, Salah.
Winning a game and losing a game is debatable.
Somebody has just said that.
I said it's debatable.
It's debatable.
Which one is debatable?
The winning of the game and losing of a game.
Okay, let's see the debate. What's it?
The first leg you could have won, but the second leg you will lose, and then you are still
so
the
we
winner.
are not talking about two separate events. We are talking about two events happening at the same time.
So winning a game, what if it's a
You can't talk about the first leg and then the second leg. These are not happening at the same time. We are talking about in one game, you can't win that game in that one game and lose that game in that one game. But you are talking about sequential games. You're talking about simultaneous games.
No, Prof, I think he's trying to say what if there's a draw?
What if there is a draw?
Yes.
In the game?
Yes.
Okay. That makes sense. But when there's a draw, then you now have an intersection, right? When there's a draw, you have an intersection. So yeah, he's got a point. Good. Let's go to Genny and Frederica.
So a functional traffic light cannot show green and red at the same time.
Okay, I agree. Depending on which country you are. Depends on which country you are. Okay, let's go to Kingsley.
Being in government and being in opposition.
Oh, it happens. Masa, some of them are political prostitutes. They will be here and be here at the same time. It happens. Let's get the last one. Frederica.
Doc, passing and failing the same exam.
Okay. Kind of agree with you. You can't pass and fail the same exam. I mean, how is that possible? So now you guys are getting mutually exclusive events. Let's move on to the next point. The next point is this term we call union of events. Okay? A union B is simply A or B. Take note. Okay? A union B is simply A or B. Remember the word or is what symbol? What mathematical symbol is or? Jenny, right. What is a mathematical symbol?
Plus.
Plus, okay, so keep that in mind. So here's the thing. When we talk about A or B, we do not include the intersection. It's very important, okay? A or B. That is critical. Now, another one is collectively exhaustive event. So let's say that we have event 1, 2, 3, all the way up to K. These are said to be collectively exhaustive. If and only if the union of all of them is equal to the universal.
So sorry, say I don't know. Maybe it's but I can't hear you clearly. Your voice is a little bit low.
Okay,
so
let's confirm from the others
this.
and see. Is that how my voice is? Is it that it's far away?
No, we can hear you.
No.
It's very clear.
Okay, so my dear, I think the problem is at your end. So
Yes,
double
it's
check.
I'll check.
All right.
Okay, I'll check. Thanks.
Right, let's move on. Let's move on. We are getting to the exciting part, and I know you guys are going to love that. Okay. So at the complement of an event, I think one of the guys, a very smart guy, gave us a prelude to that. He says that the complement of an event. Okay, simple language. What is a complement of an event? Don't be technical at all. Simple language. When we say the complement of an event A, what does that mean? By the way, the way to write a complement is A bar. When you write it A bar, that is what we mean by the complement of A. So A bar is a complement of A. What does it mean? What is a complement of an event? It's very easy. Oh, the lady was right that you guys cannot hear me. Can you guys hear me?
Doug, we can
Yes,
hear
we can
you.
hear you.
Oh, okay. All of a sudden there was silence, so I thought we were in a cemetery. Yes, I mean.
Well, the inverse of A.
Yeah, we are using two mathematical terms. Make it simple. Explain it to a 6-year-old child. Let's go to Selassie.
Doc, all the values that are not found in A.
Simple. You see, this one, a 6-year-old child will get it. Excellent. Okay. Einstein says that if you cannot explain to a 7-year-old child, you don't understand yourself. All the values that are not in A is said to be the complement of A, and it is denoted by this symbol A bar. Okay. So look at it. You see, A is a circle, and A bar is anything outside a circle. That's a complement of A. Keep that. Okay. Let's look at a couple of examples. This is a real-life example, and this will test your brain. I know a lot of you were using the toss of a coin, but we are going to look at the roll of a die. Please write the following information down. When you roll a die, how many numbers appear or are possible to appear?
6.
How many numbers? 6. So this 6 is the sample space. But I want us to pause a little bit. Hold on to the die. Tell me some other games we used to play apart from the die. Oh, by the way, the die, what do we call it? What do you call it? There's a very funny name for it. Beautiful name.
Ludo.
Ludo. Ludo. Okay. Those of you who have not played Ludo before, please try and play it, because it's a very tension game. There's a game I have in the UK. It's called Nuno. Nuno. Okay. All right. What other games do you know? I'm not talking about the video games that are happening these days. We used to have great games. You remember those great games? Give me some of the names.
Monopoly.
If you're a computer child, you cannot mention some of these good games. Owari. What else?
Dummy.
Dummy. Very good. That is a draft.
Spa.
Spa. Very good. We shall look at the Spa very soon. By the way, the Spa is not usually called Spa. What's the name of that game?
It's called cards.
A deck
Decking
of cards. Very good.
Mm.
But at least we have that beautiful name we call Spa, which sounds well. And for her to know about it means that she has been playing it. What is another game you know of?
I think, is it Snake and Ladder?
Snake and Ladder. Very good. Very good. That one is also used on a similar thing like Ludo, when you turn it the other way around. You remember the good old days? These days, internet has spoiled you all. You spoiled. You don't play good games. Okay? When was the last time you played Ampe? And Clifford said Ampe, even though he's a boy. I can imagine him play. Okay? Ampe. Okay. Chess is still good, but there's a game called Go. Go. It's a very powerful game. It's the most difficult of all games of the chess arena. Powerfully played in China. And artificial intelligence has created the AlphaGo. Go and Google and watch the video, the AlphaGo. It beat the 19-time world champion machine. Yeah, beat the guy who has been a champion for 19 years. The machine beat the guy, showing that the machine is more intelligent than the guy. AlphaGo. Okay, that's it. But we have other games that you can look at. Do you remember the games where you use the sardine, the thing you used to, open the sardine to play? You remember Countess as well?
Yes.
Yes.
Not the one that you count. Do you know the one I'm thinking about?
Yeah, the
Countess ball.
Yes.
I know, I'm talking about the one where you roll with your finger, with your hand.
Yeah, you live to cover the other one.
Exactly.
Yes, yes.
And then you make sure you cover the other guy's own with it. And then you collect his items. And then there's also another one for sardine. You have the sardine. the thing you used to open Titus sardine, then you roll it to the right. That thing. Who remembers this kind of thing? Were you born in the land?
This sardine one day, it doesn't sound familiar.
I know. I know it doesn't sound familiar. But come on, somebody should remember. What? Yeah, what?
Dog, we are Gen Z, so we don't know.
Ah, okay. You are the Gen Z. Well, we got to learn some of these things because it's those things that have made some of us, super powerful. Okay. Somebody says rubber band game. What is a rubber band game?
Tie.
Ah,
Yeah, that's
Hits the wall.
somebody says chaskele. You remember chaskele?
Yeah.
hide and seek.
Oh, Jimmy. Oh, I love this thing. He says petenge.
Hide and seek.
I think I remember that game. Cha-cha. It's also, you remember Ajana 1? Okay. All of these are great games. Pilolo, excellent. See, you remember? Likoto, very good. You remember Likoto as well. All of these are great games. Go find them. Your kids must start getting excited with some of these things. What is Zanzama? Solace, what's Zanzama? I've never heard of that. Is there a game called Zanzama?
Oh, probably.
Zanzama.
If you don't know it, you've missed.
Zanzama, is it a northern game?
No, when we were kids. So before you sit down in class, you have to say Zanzama, else you receive a knock on the head.
Yeah.
Oh, wow.
Prof, you were DB. That's why you don't know this one.
Yeah, maybe. But meanwhile, I saw that Kashao. Joy. I dyed blue jeans at Kantamatu for 15 years. So I'm not that much of a DB. I don't know. But we've come out clean on the other side. Anyway, Alewa. I remember Alewa. Okay. So now let's settle on the roll of a die. You have these numbers. If I were to ask you that, let me give you some scenarios. So you're going to pick an event. Let A be the event of the number rolled is even. Okay. So let A be the event that the number that rolled is even. Who can tell me the elements of A? Who can tell me the elements of A? Let's go to Christy. The elements of A, Christy.
Is 2, 4, and 6.
2, 4, and 6. I'm sure you all agree with that. Let's go to the next event. B. B is the event that the number rolled is at least 4. The number rolled is at least 4. Who can tell me that? Please be participatory because I actually give marks to those who participate than those who just sit behind. I won't lie to you. That's how I do my work.
4, 5, 6.
Please, you have to raise your hand and I'll call you. Otherwise, the whole thing will be a market square. Philip.
Say 4, 5, 6.
4, 5, and 6. Good. Okay. So you got all of these 2 events as you can see on your screen. Now, you have these 2 events. If I were to ask you to find, and listen carefully, find the complements of A. Who can tell me the complement of A? Be careful. Can tell me the complements of A.
1, 3, 5.
Raise your hand. Don't talk in the air until I call you, please. Otherwise, if everybody talks, we'll not get. Naki, Vanessa.
1, 3, 5.
1, 3, 5. What are the complements of B? What are the complements of B? By the way, Vanessa, that was correct. Complements of B. Fatima.
1, 2, 3.
1, 2,
3.
1, 2, 3. Okay, very good. Now, let me ask you. Samuel. Samuel, your hand was up. Or you finished?
Yeah, we are done.
Okay. So what about
Intersection.
What about, no, I'm not using intersection. What about the complement of the complement of A? Be careful. The complement of the complement of A. You can tell.
Complement of A.
Please raise your hand.
So,
These are some of you are enjoying it. Okay. Yes, Philip.
Says 2, 4, and 6.
Again?
2, 4, and 6.
Very good, very good. Now let's go to the intersection of A and B. The intersection of A and B. By the way, these first ones that you got, these are the answers. The intersection of A and B. Talk some more, Valentina.
4, 6.
4 and 6.
4 and 6. Good. The intersection of A and A complement. The intersection of A and A complement.
And A complement.
Please raise your hand, okay, and let me call you. Otherwise, everybody will be doing what you are doing. The intersection of A and A complement, right?
Please, there's no intersection.
So what is the name?
0.
No, you can't say 0. 0 is a number. Let me go to
Now.
Samuel.
It's an outset.
It's an outset. That's it. Keep that. Keep that. Keep that. These are fast moving. What is the intersection of A complement and B complement? The intersection of A complement and B complement. Be careful. Be careful. Root. Root is vanished. Let's go to Clifford. Selassie.
Doc, 1 and 3.
1 and 3. Very good. So guys, you got to know most of the things that we are talking about. Okay. I didn't talk about A complement intersection B. Okay, that you should get that. What is B complement intersection A? You can tell us. Intersection A. B complement intersection A. What would that be? Zoe.
2.
2. Are you sure?
Yes, please. B complement intersection A is 2.
Is that true? I'm asking, is that true, to see what other.
Yes.
Affirmative.
Good.
That's very true.
All right, let's move on. What is a union of A and B? What is A union B? No. Yeah, what is A union B? Be careful, it's not straightforward. What's A union B? Vanessa?
2, 4, 5, 6.
Okay. What is A complement union B complement? What is A complement union B complement? You can imagine you have all of these things to do in 10 minutes. Yes, Ruth.
Okay, Doc. 1, 3, 1, 2, 3, and 5.
Very good. Okay. Now, what is A union B complement? A union B or complement? What is A union B or complement? Yes, Samuel. Samuel.
Sorry, I was on mute. That's 1 and 3.
That's what?
1 and 3.
1 and 3. All right. So, guys, you should get to know most of these things that we've been talking about here. Okay, I didn't ask this last one, but this is a very powerful point. Okay. A union B, A complement union A. A complement union A. A complement is on top, there is 1, 3, 5. Okay. A is 2, 4, 6. So you get 1, 2, 3, 4, 5, 6. That's it. That's the universal set, actually. All right. So let's look at mutually exclusive events with this example here. Okay. A and B are not mutually exclusive. Who can tell me why? A and B are not mutually exclusive. Who can tell me why? If you're able to tell me why, you are here. Philip.
So please, because there is the possibility of having some events both between A and B. That is 4 and 6.
Excellent. That's your answer. I agree with your answer. Okay, 4 and 6 are common to both. Okay. Now, let me ask you, A and B, are they collectively exhaustive? Is A and B collectively exhaustive? It's an easy question, but it's a tricky question. Is A and B collectively exhaustive? So I will ask you this thing. Is A and B mutually exclusive? Is A and B collectively exhaustive? Someone.
So they're not collectively exhaustive because the union of A and B still has 1 and 3, which are not included.
Exactly. Okay. So you can see that 1 and 3 are not inside that, and therefore is not collectively exhaustive. Now that gives you an idea of what a collectively exhaustive event looks like. Okay. Now let's go to some postulates, some rules of probability. We know this already, but let's recap. A probability is the likelihood of an event coming. That is probability. The likelihood of its coming is certainty. The likelihood of it not happening is not certainty, but you can't use it, it's not certainty. Let's get a better word. The potential of it happening a lot is 1. The perfection of it happening is 1. The imperfection of it happening is 0. So the probability being equal to being between 0 and 1 inclusive means that the thing has got certainty or impossibility of it happening. So while zeros will imply impossibility of it happening, 1 will imply possibility of its happening or certainty of its happening. So you got to understand that the probability is between 0 and 1. So the probability of an event not happening is 1 minus the probability of the event happening. Take note. The probability of the event not happening is 1 minus the probability of an event happening. Not happening is happening. There are 3 approaches to calculate probability. The easiest one is the classical, then the relative, then the subjective. Let's look at a bit about the classical. Now, the classical assumes that within the universal set, anything is likely to occur. So the probability of an event A is the number of outcomes that satisfy the event relative to the total number of events, total number of outcomes in the universal set or in the sample space. So it is like the part relative to the whole. The part of that event you're dealing with relative to the whole. And it requires that you count the outcomes, practically count it. The relative probability, the frequency probability, that one is the number of events in the population that satisfy event A. Now, what is the difference between them? The probability of A relative deals with the number of events within the population that is satisfying the event A divided by the total number of events in the population. So what do you see as the difference between the relative and the classical? Who can tell me? The relative and the classical. I have this question somewhere. What do you think is the difference between the relative and the classical? I know you guys were getting excited a bit, but now it looks a little bit abstract. Find out the difference. Okay, you can see the difference within a keyword that will satisfy that. Find it, find out. Subjective probability is very easy. It's an opinion. Opinion about the probability of the event happening. It's just a guesswork. You don't want to do that. I'm going to be wrapping up I'm going to get into the main thing for today, And that is the rules of probability. Rule number 1 is called a complement rule. The complement rule says that the probability of A complement is 1 minus the probability of A. Take note, put it down. We're going to look at something very soon. So if you do change of subject, it means that the probability of A plus the probability of A complement will give you a value of 1. Fairly simple. Very simple. Next one, addition rule. Addition rule says that the probability of the union of 2 events is blah, blah, blah minus the intersection. The probability of the union is something plus something excluding the intersection. So the probability of union A union B is the probability of A plus the probability of B minus the probability of A intersection B. Who can tell me why that A intersection B has to be subtracted? Who can tell? Remember our first Venn diagram. I'm getting the creme de la cremes of this class, the alphas and the omegas of this class, the gargantuan gagamamus of this class. Those people who are able to elevate your mental gymnastics, people who vomit intercontinental ballistic Kosovoic atomic missiles. These people have consistently demonstrated their presence of their essence.
Hey.
Right, Philip. Okay, and I think consistently has also been one guy. But for this very tough question, Marion has joined them. Marion, tell me the answer.
Okay, so the reason why we have to take that out is because if we don't take it out, there's going to be a duplicate representation of the intersection between A and B.
Why? Why?
Because A has, so example, if I have a set of 5 in A and a set of 5 in B, maybe if my intersection is 2, if I add A and B, the 2 in A and the 2 in B are going to add and duplicate. So then you have to take out 1, which is the intersection of A and B, to bring it a balance.
Perfect. Very good. Very good. Okay, you've done quite well. Okay, let's take this story now to understand all that we have learned. Guys, do you remember a deck of cards? Do you remember a deck of cards? Who can remind me or remind us of the number of items in a deck of cards? Well, how many cards do we have in a deck of cards? How many cards? I just want you to understand it because there's a lot of things you're going to learn here. How many cards do we have in a deck of cards? Oh, you forgot your name. Don't worry.
A 50 something.
You are guessing or you are telling us by raising your hand. Kingsley.
52.
It's 52. Okay. What are the names? Do you remember the names of the deck of cards? One that looks like, okay, they are proper names and they are local names you used to call them. You remember those things? Okay. Salasi, give me some.
So we have Kalo.
Kalo. What is the proper name for the Kalo? Who can tell us? Oh, by the way, the Kalo is a what color?
So I think red.
It's red. What is the proper name, the professional name for the Kalo?
It's a spade.
No, that's not Kalo.
That's the hat.
That's that. Maza. Find some water. Find some water. And come back again. What is the proper name for the Kalo? Watson.
A diamond.
Diamond.
Prof, is it a king?
Oh, Koviadu. Watson has already confirmed the diamond, and we are talking about king. Now, what is another one that we have, another card, apart from the Kalo or the diamond? Apart from the Kalo or the diamond, those who are stealing, I know what you're doing behind the scene. Stop Googling. Okay. Salasi.
So we have the hat.
The hat. Okay. And what name did we use to call it? Who remembers the name? Vanessa.
No, I was going to mention spade. I don't know the name.
You're going to mention spade. Okay, let's deal with the hat. By the way, the hat is made up of what color? It's what of all color? Quickly. What color is a hat?
Red.
It's red. And what name do we call it? Do you forgotten that you used to call yet? No. It's yet. We used to call it yet.
Yes.
See, you are telling me that I'm a computer child. You people are more Gen Z than me. All right. So we've spoken about a diamond and now the hat. Both of them are red. Now let's go to the blacks. Okay. The first black is what? Kinsley.
Kulain. Is it Kulain? I'm not too sure.
Kulain. Very good. Kulain. But then what's the proper name? What's the proper name? Samuel.
The speed.
Hmm?
Or was it the speed?
Samuel, you are guessing. You are guessing. I think you should come back again. Yes, Kinsley.
Yeah, club.
Yeah. So you people are asking, is it a? It's like people have never eaten long time. You've never played these things long time. You've been using some fake names. You call it what? Kulain. I mean, if you call it a team Kulain. So how will you not know? How will you know that it's a club? Oh my goodness me. Now let's go to the last one. What's the name of the last one? I want you to think before I show you. Last one, Selassie.
So the spade.
The spade. And we used to call it what? What do you call it? Spy.
Yes, spy.
The spy. That's a real spy.
That's a real spy.
That's a real spy. Oh my goodness me. Somebody is lost. He is somewhere in the valley of Hinnom. Lost, completely gone. You know. And now let's use the proper names. Let's use the proper names. Now I want to show you something, guys. Okay. I want to show you something. The proper names. The proper names. You are talking about the spade. I mean, from here, you will notice that the first one here is a hat, okay, is a club, is a diamond, then the spade. Okay. Now for each one of them, you have different groupings. You have the numbers. First, you have the S's. How many S's do we have? How many S's?
So I think.
Don't think. Guys, there are 52 cards, so don't think at this stage. Vanessa?
4.
4. There are 4 S's. Please keep that. If you are not taking notes, you are behind. Yeah, because we are going to use this a lot, and we use this a lot in most of my questions. Okay. So you have 4 of the S's. How many numbers do we have? Numbers, not S's, but numbers. How many numbers do we have? How many of the numbers do we have? Apart from the S's, we have numbers from 1 to what? How many of the numbers? Selassie?
26.
No. I mean, for each group, how many numbers do we have? Elsa?
It's 1 to 10.
Yes, 1 to 10. Elsa, this is the first time I'm hearing your voice, okay? Okay, keep coming. So you got 1 to 10 for each of these circled types. You got 1 to 10. And then after the 10, we have what? How many jacks do we have? How many jacks? So that's...
Say 4.
How many queens?
4.
How many kings?
4.
Guys, it's been a long time you really looked at this. Now I want to show you something. Get to know all these things. Here you are. This is a deck of 52 cards. What you see on your screen is a deck of 52 cards. We use it a lot. Probabilities. Magicians use this a lot to trick people because they understand probabilities. So, let me ask you a question. Let me ask you a very poignant question. The question is this. Let event A be equal to the card is an essay. Let event A be equal to the card is an essay. What will be the value of that? What will be the value of that? The card is an essay. Sarasi?
Say 4.
4. Let event B be the fact that the card is from a red suit. Red suit. Now that one is easy. Red suit. Come on, you know that. Red suit. If you get this basic principle, then we can go. Okay. There are 52 cards. Okay. For us to get 52 cards each, you must have 13, 13, 13, 13, 13. So what is the problem? I mean, what event B, the card is from a red suit. What is the number there? Joseph?
96.
26.
So that'll be 26.
Okay. What is if I had an event where the card is a black suit, what would that be? A black suit. Joseph?
Still 26.
What about a club black suit? A club black suit. A club black suit. What's it?
13.
Okay. Guys, follow the trail. Follow the trail. Now let's go to the real questions. Okay. Oh. Let me rather ask you this in the form of a question than first showing you the answer. So here I have a question for you. Still on this probability. I want you to calculate the probability of a red union essay. I want to write it here. Calculate the probability, okay, of red union essay. Who can tell us how to go around it? Now give some idea about how to go around it. Red union essay. So this, first of all, this red union essay will be probability of what? Jenny?
So I think it will be the probability of the red plus the essay, then you minus
the essay. What do you mean by the essay? Number of essay or probability of essay?
Probability of essay, then minus the intersection.
Okay.
Like as we were saying earlier on.
Good. So what he is saying is that it's going to be Yes, a second. Yeah. It's going to be the probability of the red, and you got to learn to write that. Okay. Plus the probability of the essay minus the probability of the intersection of the red and that of the essay. Is the intersection. Okay. So now let's first of all find the probability of the red. The probability of the red will be what over what? And by the way, remember we are using, by the way, what are we using? Are we using classical probability or relative frequency probability? Okay, you should know that. I've already asked you to go and find out on that. Okay. But what is the probability of red? You can tell us. The probability of the red. Jenny?
26 over 52.
26 over 52, guys. Take note. The probability of the red is going to be 26 divided by 52. Why? Because there are 26 of the cards that are red. If you take the hat and the diamond, each one is 13, 13. That is 26. Now, that's the first one. Probability of the essay, what would that be? probability of the essay? Philip.
So that's 4/52.
4/52. There's no question about that. And then, according to the analysis, we should subtract the probability of red and the red intersection essay. What would be red intersection essay? Be careful there. Be very careful. And why would you choose that answer? I'm not interested in that. I'm not interested in the answer because you can guess. Joseph.
So there's an essay in all the suits, and in this case, we need the red of it. So that would be 2 out of the 4. So that would be 2/52 intersection.
Okay. I can guarantee you that is incorrect. The probability of red intersection essay, what is that? Explain it to me, Salasi.
So there are 4 essays, and then 2 are red and 2 are blue, black, sorry. So
very good. I like the way you started. Guys, listen to him because he started on a very fine footing. He says there are 4 essays. 2 of those 4 are black. 2 of those 4 are red. Please continue.
probability that of the red intersection A will be 2/4, which is 1/2.
You tried, that's why I paused, but you could not end it gargantuanly. Oh my goodness me, I need someone to bail us with an interpretation. What is the probability of red intersection? What does it mean? Jenny?
So as he started, there are 4 essays, and out of the 4, 2 are black and 2 are red. So if we want to find the let me say the intersection of
By
the
the
red.
way, Jenny, before you continue, help us to understand by intersection, what do we mean? Something that is common to both, isn't it?
Yes.
Good. So let's use with that.
Okay. So let's say in the essays, there are 4 essays. So if we want a common color, which is red, there are only 2. So that would be like if, let's say, we were just looking for just that red intersection A, that's when we'll use the 1/2. But in this scenario, we're looking for the probability of red intersection A. So that would be 2 over the whole 52.
Okay.
So the 2 reds over the total number of cards we have, that's 52.
All right. You missed something because it's the question. The point we are doing is that we are looking at the probability of red intersection essay. Let's try to get it. Hayford.
Okay, sir. So as they were rightly saying, it will be 2. Hello, sir. Can you hear me?
Yes.
Yeah. So for the A's, we have 4, and like they were saying, 2 are black and 2 are red. So it means that we are looking at the 2 which are red, and within those 2 that are red, we also have 26, which the entirely are red suit. So it means that out of these 2, we can find these 2 within the 26, which are red suit. So that intersection will be 2/26.
You came closer and then you whitewashed it. Because what others have said is correct, but I just wanted to be sure that people know what it is. Okay, and now people are changing the correct answer. So finally, who can tell us the probability of red intersection A? It's been said, I was just trying to be sure that people know exactly what they were saying. What is the exact probability of red intersection A? Someone has said it. I think 2 people have even said it. Who can summarize it? 2 of you said it. Yes, Jenny.
It's 2/52.
It is 2/52. And why it is so is already been explained. I was just trying to be sure that you all understand that. Okay? If you look at the number of reds that are S's, there are only 2 out of the whole 52. So now let's substitute this probability of red plus the probability of S's minus the probability of red intersection S's. Find the value and let me know. So you have 26, okay, over 52 plus 4 over 52 minus 2 over 52. What will you get? What will you get? You know, if you are here, you haven't spoken, you have to tell us. Yes, buddy.
28 over 52.
So you get 28 over 52. Ladies and gentlemen, this 28 over 52 is the answer you get for the probability of red union S. Red union S. I'm telling you, I can ask over 100 questions on this story alone. You have to get the facts very well. Okay, so that is how you attack this very question. Let me just wipe out this, then we can look at the result. So that is how you look at it. Okay, you look at red, probability of red union S. This is what we call the addition rule. The addition rule requires you to take out the intersection to be able to get the entire. Now, the next thing we are going to look at, and is the last one, is known as the conditional probability. Conditional probability. There's a lot of beautiful things here that I want you to note, because it is from this conditional probability that we can achieve the Thomas Bayes theorem. A word conditional, who can give me another word for it? I want you to understand this very well. The word conditional. Conditional means what? Give me another synonym, a synonym for conditional. I think my coming is conditioned or conditional on, what does that mean? Conditional. Now let's get the English writers. Miss Watson.
It can also mean it's dependent on something.
Good. Conditional is dependent. What else? What is another word that comes to mind apart from dependent? Joseph.
Say, you can say it's contingent on.
I love that. It's contingent on that something. Now let's go a little bit slow. Let's get into the realm of a 6-7-year-old child. 6-7-year-old child. Kinsley.
It's determined by.
Determined? That's a little bit tricky there.
No, determined. Sorry, determined by.
Determined by. Someone says provisional. Determined. Yeah, I'll go more with determined than provisional. Okay. Is influenced. Is influenced. Is as a result of. Is influence. Is as a result of. Okay. So with that in mind, a conditional probability is that likelihood of one event given that the other has already occurred. Guys, can you tell me real life situation that presents conditional probabilities or conditional probability terms? I'll give you one. Okay. The ability to get pregnant is dependent or conditioned on being a woman. The ability to get pregnant, first of all, depends on you being a woman. That is a conditional event. That is conditioned event. Who can give me two events where one is conditional to the other? One is conditional to the other. Don't think too much. When you start thinking too much, that's when you know you're wrong. Conditional. Conditional, come on. Philip.
Please, voting depending on your nationality.
Voting depending on your nationality. Very good. Next. Next, Selassie.
Doc, to be a Roman father, you need to be a man.
I like that. People are strict too. People are very strict. Very good. What other ones? What other ones comes to mind? Portia.
Prof, please, I also say traveling by road also depends on cars.
Oh, you can use bicycles. You can use motor.
Long distance.
Or you can still use cars. You can use articulator motors. Motors can even go further long distance.
Oh, okay.
So get me something else. Menina.
For me to attend the class depends on the condition of the weather.
Oh, yeah. You mean the weather has to be what before you can attend the class? That if it's raining, you won't attend. Give me proper condition, not this kind of caricature conditions. Christy?
So for a Ghanaian to be able to travel to the US, he or she must have a visa.
Which visa? Ghanaian visa?
No, US visa.
US visa, very good. Okay, good. So your travel to US is conditional on you getting a US visa. Very good. I like that. Ruth, it's not debatable.
Okay, Doc. So I think before you gain admission to the tertiary level, it will depend on your results in high school.
Okay, it doesn't depend on who you know, right?
Probably no.
Okay, okay, good. Bertha, give me one.
Well, you need to pass your papers before you can graduate from the university.
Very good, very good. Michael?
Winning presidential elections to have 50+1% of the votes.
There's no doubt about that. Your mind is all election. All right, very good. So the probability of an event A giving event B, okay, that's what would be the conditional probability of event A giving event B is equal to the probability of A intersection B divided by the probability of B. Now watch carefully between the one at the top and then the one at the down. Okay, the conditional probability of A giving B and the conditional probability of B giving A. What is the difference? Because something is the same. What is the difference? Something is the same with the answer. The only different thing is what? Is the probability of the two events. Do you realize that? The only difference is the probability of the two separate events, not the intersection. The intersection is always the same in both cases. Please, we'll use this one to generate the base theorem next time, but just understand this very concept. Okay, next one. Let's take a typical question. And this question, once you can crack it, you will be able to get everything. So, of the cars on a used car lot, 70% have air conditioned AC, 40% have CD, 20% have both. What is the probability that a car has a CD player given that it has AC? Do that. And privately send me your answer. What is the probability that a car has a CD player given that the car has AC? Watch the order. Find that and let me know. You have some 3 minutes to give me that. All right, so what is the probability that a car has a CD player? Now, the probability that a car has a CD player, given it has an AC. So what it means is that we want to find the probability of CD given AC. The probability of CD given AC. Now that will be equal to the probability of CD intersection AC. You can see it from here. The probability of CD intersection AC divided by the probability of AC. The probability of CD intersection AC. That's how it to be. Probability of CD intersection AC. That will be the numerator. Divided by the probability of AC. This will be equal to the probability of CD intersection AC was given as what? You can tell it.
Doc.
Yeah.
20%.
20%. That is 0.2. The probability of AC was given as what?
70%.
70%. Okay. So if you look at it, it's not difficult at all. It's 0.29 on average. If you check it, that's going to give you 0.29 in total. So that is how you calculate the probability of CD into bracket AC. Now, technically, it will be the answer you see down here, but I've rounded up to be able to get the feel and the capture of everything. Okay, there will be a situation where you will have to calculate the percentages yourself. Okay, who can tell me, do you think that the conditional probability of AC given CD, will it be the same as this? The conditional probability of AC rather given CD instead of the other way around, will it be equal to this?
No, Prof.
Explain why. What will make it not equal?
Because the AC.
What value?
70 will be divided by 40. 20 will be divided by 40.
Exactly. So you replace the 0.7 with 0.4, and that will change the score. All right. So you should try that on your own. Okay. Next time we meet, we are going to look at multiplication rule. Okay. And then we'll apply the multiplication. We'll look at the joint and marginal probabilities. We'll look at the decision tree, and then we'll finally look at the Bayesian statistics. The Bayesian statistics. Ladies and gentlemen, that brings us to the end of the entire caboodle.